In this video, we solve problem number 6 from quiz number 1 from the spring 2021 semester. This is from the elementary differential equations class, that's math 2613 at Tulsa Community College. We're asked to find the general solution of the first order differential equation, and we have this right here. And we know it's first order because you have a function of x. Well, we know it's a first order linear ordinary differential equation because we have a function of x times our derivative plus a function of x times the dependent variable equals a function of x. Since that's the case, we want to start by writing the differential equation in standard form. So that means we want to take this entire equation and divide by x. And remember what standard form is. Sometimes I've heard it called general form. It's just where dy dx has a coefficient of 1. So you have 1 times dy dx plus a function of x times y equals a function of x. And these x's reduce. So we end up with dy dx right here. And then this can simplify. We can take 2x and divide by x. That'll give us a 2. And then we'll have a minus 1 over x there. And of course, one of those x's will reduce, and we have a 9x squared times e to the x on the right-hand side. So once our differential equation is in this form, then the next thing we do is we prepare to find our integrating factor. Our integrating factor involves the integral of p of x. It's e to that power, where you just choose a particular constant of integration. So we start by finding the antiderivative of p of x. So we identify p, and we compute its antiderivative. So the antiderivative of 2 minus 1 over x. So we'll get 2 times x. The antiderivative of a constant with respect to a variable is that constant times that variable, minus the antiderivative of 1 over x, which is natural log of the absolute value of x plus c. Now we're going to take e and raise it to this power, and we're going to use that as our integrating factor. Now we don't need infinitely many integrating factors. We just want one, so that when we're done multiplying by it, the left-hand side is the derivative of y times the integrating factor. Since we only want one integrating factor, we can choose that c to be 0. Okay. Then our integrating factor is this. It's typically denoted by mu of x. It's e to the integral of p of x power. So you have e to the 2x minus natural log of the absolute value of x power. Now, since you've got a sum or a difference up here, you can use exponent properties to rewrite that. If you have x to some power times x to a different power, you add the exponents. That works backwards as well, even if the base is not your variable. So we can call this e to the 2x times e to the negative natural log of the absolute value of x. Now, I really want to cancel that e and that log, but I can't do that. Those don't undo each other until I get rid of that negative 1. So I have to remember this property from algebra. If you have a constant in front of a logarithm, you can bring that constant inside and make it a power for what's inside. So this is actually this. And then because the natural logarithmic function and the natural exponential function undo each other, you're just going to get absolute value of x to the negative 1 there. Or if you prefer, this is e to the 2x all over the absolute value of x. Now, obviously, x cannot be 0. Now, if we're trying to decide whether we want x to be positive or negative, we would typically look at the initial conditions. But we weren't given an initial condition. We were just given an ordinary differential equation. with no initial conditions. So we can just assume that x is positive. That's going to be fine. If we wanted, we could assume that x is negative. That would work as well. We just can't allow x to be 0. So we'll say that the integrating factor is equal to this, and we're going to choose our interval of existence to be 0 to infinity. Okay, so now that we've got our integrating factor, we want to multiply the differential equation by the integrating factor. So we're taking our differential equation, which was in standard form, or which in standard form looks like this. And I don't remember what that right-hand side was. It was just an e to the x. And we're multiplying that by e to the 2x over x. And then we want to simplify from here. So you have e to the 2x over x times dy dx. And I would recommend simplifying this. I'll probably just distribute the 1 over x through. So this is e to the 2x times 2 over x minus 1 over x squared. And one of the x's will reduce over here. So we have 9x, and then e to the 2x times e to the x. You just add the exponents. That's going to give us an e to the 3x. Now, if you've done everything correctly, the left-hand side should be the derivative of y times the integrating factor. I didn't need to do that in red. It's okay. So you want to recognize that the left-hand side is what it's supposed to be, or you can check that the left-hand side is what it's supposed to be. Oh, if it's not, if this is not the result of the product rule applied to this y times integrating factor, then you've done something wrong. Usually it's a little algebra error up here, or perhaps forgetting a negative when you were identifying your p of x or something like that. Remember what this is. This is operator notation. This says take the derivative with respect to x of this times this, and that's a function of x. It's implied. Y is a function of x, and we're looking for it. So according to the product rule, we should get the derivative of the first times the second. That's right there. So we're good there. Plus derivative of the second times the first. Well, the first is right there. So the claim is that the second function, the derivative of the second function should be this. Well, we could write the derivative of the second function this way pretty easily if we write the second function differently and then use the product rule. So I think I'll do that. You could also use the quotient rule and then simplify later. I think I just changed my mind. I think I'd rather use the quotient rule. Now, according to the quotient rule, we get the bottom function times the derivative of the top function. The derivative of e to the 2x is e to the 2x times the derivative of the inside, which is a 2. So that's low d high minus high d low. The bottom function is just an x. Derivative of x is 1 over low low. So that's x squared. And then you see that you've got an e to the 2x in common up here, so you can factor that out. And you're left with 2x minus 1 times that all over x squared. And then if you simplify further, you could take this and divide it by x squared. And then take the negative 1 and divide it by x squared. And one of those x's will reduce. And you get this. And that is exactly what we have right there. So the left-hand side is the derivative of y times the integrating factor. So we know we're on the right track. That means we're 2 steps away from getting y by itself. We've got this derivative on the outside. To get rid of the derivative, we will anti-differentiate. We'll have y times the integrating factor over here equals this antiderivative. Now u substitution doesn't work because the derivative of this inside function is just a 3. It's not a 3x, so it's not going to work. But I still have a product, so I'm thinking if u substitution doesn't work and algebraic manipulation doesn't work, because you can't really simplify a polynomial times an exponential, integration by parts is the way to go. So let's let part of this be u and everything else is dv. We'll let u be our polynomial, dv will be everything else, and then remember this formula. The integral of u dv is uv minus the integral of v du. Now you can do this with the 2x2 table if you want. I prefer to use tabular every time u is a polynomial. It just makes it really easy. So I think I'll do that. Oops. So we put u in this column and dv in this column. Typically when we use tabular integration, we don't list the dx over here. So we'll have u equals 9x and dv is e to the 3x times dx, and we usually leave that off. Now, when you're using tabular, you differentiate this column until you get 0. Derivative of 9x is 9, derivative of 9 is 0. And then you anti-differentiate in this column until both columns have the same number of rows. So you're going to anti-differentiate once to get that. Now, if I were taking the derivative of e to the 3x, I'd have to multiply by 3 because I'm taking the derivative of the inside, that's the chain rule. When we're taking the antiderivative, to undo that multiplication by 3, we divide by 3. And then when you anti-differentiate again, you're going to multiply by a 1/3 or divide by a 3 again, and you get that. And then the result of tabular integration by parts is this. You multiply across this diagonal, that's u times v. A 1/3 of 9 is 3. And then you subtract the integral of v du. The integral of v du is right here, and the integral of v du turns out to be u times v minus the integral of v du. Yeah, there's a reason why all those diagonals work. But we multiply across this diagonal, we multiply by +1, and then we add, and then we multiply across this diagonal, we multiply by -1, and then we add. So the 9 times a 1/9 is 1, and then we multiply with the -1, so it's going to be a negative e to the 3x plus c. And all of this is equal to y times e to the 2x over x. Okay, now we're trying to get y by itself. So we will multiply by the reciprocal of this on both sides. Or if you prefer, you could call that an e to the negative 2x. That's fine as well. These guys will reduce. And we'll get this. So I have y equals 3x times e to the 3x minus e to the 3x plus c. And remember, we just multiplied by x divided by e to the 2x. Or you can bring that e to the 2x up to the numerator, make that an e to the negative 2x. And then if you distribute, you're going to get this. 3x times x is 3x squared. E to the 3x times e to the negative 2x is e to the x. And then this times this, you're going to have a negative x. E to the 3x times e to the negative 2x is e to the x. And c times that doesn't simplify much, so you're going to leave that alone. So that is our y. That's our general solution. And earlier, we said that y or x had to be non-zero, and we just chose for x to be greater than 0. So we can use the interval from 0 to infinity. But we could have easily chosen the other interval from -infinity to 0, and that would have been fine too. So that is our general solution. And that last step was solving for y. And you can think of that as dividing by the integrating factor or multiplying by the reciprocal. You're just trying to get rid of this piece. And in this case, we multiplied by the reciprocal. We stated the general solution on a particular interval of existence. Let's go through the method one more time. First, we write the differential equation in this form. Get the 1 times y prime plus a function of x times y equals a function of x. Then we identify p, that's the function multiplying y. We compute its antiderivative. We choose the c to be 0 because we don't need infinitely many integrating factors. We just want the 1. And then we find our integrating factor. That's it, but we need to simplify it. So we use this property to break it up this way. We use this property to get that negative inside the logarithm. Then we use this property to simplify that further. Then we get here. And then we say we really don't want the absolute value. So we will drop the absolute value, and that's legal as long as x is positive. If x is negative, then the absolute value of x would be negative x. But we're about to multiply the differential equation by this anyway, so the negative sign's not going to matter. So we have this original differential equation, and we're going to multiply it by the integrating factor. And that gets us here. Then, of course, we simplify. And then if we've done everything correctly, the left-hand side should be the derivative with respect to x of y times your integrating factor. So that's an opportunity. I would always write that down, and then I check and make sure it actually works. Derivative of the first times the second is right there. Derivative of the second times the first should be here, which means that this piece, this factor multiplying y, should be the derivative of your integrating factor. So we compute the derivative of the integrating factor and we compare it to this. If they're the same, then you know you've done everything correctly. Okay, so we checked it out and we did do everything correctly up to that point. Trying to get rid of the derivative, so we anti-differentiate. This time we had to use integration by parts or tabular integration, either one, to evaluate that integral on the right-hand side. And then we solve for y. And then finally, we simplify and state the general solution on an interval of existence, the maximal interval of existence.